When dealing with black color solution, observe there is a precipitation of silver chloride from copper chloride and a small amount of contaminant metals into zinc chloride, nickel, iron, gold, aluminium, bismuth, tin, less than 5%. Precipitant is the greater brown color, most likely cement silver. 60-40, black solution, cement is silver. The reaction preceding the black color was sodium hydroxide crystals. Urea probe and brown sugar crystals poured in and stirred at 15 degrees C. The solution was a white cloudy grey precipitant with an off-white cloudy solution above it and mixed in with another separate solution to create an amalgam of almost identical solutions in the same batch of a battery of cells. These cells were combined. Some cells in glass showed white-grey precipitant, most likely silver. Some were pale blue-green solutions. Some were cloudy white clear solutions. All battery cells contain domestic cloudy ammonia solution as the source of ammonia. An extra tap water was added to divide the separation of precipitant isolation. What can be easily done? Clarify the black liquid. Once the precipitant has been collected from the battery of silver chloride, copper chloride cells, what is likely to be able to be further precipitated using what method? Instinct suggested that the addition of water may help dilute the black color of the solution. However, with the addition of more tap water, it has only extended the amount of black solution, with little to no impact on the color of the precipitant in the solution, with very little indication except for one of two cells which are only marginally more clear. And in the cells that have slightly clarified, the solution appears chocolate brown. The precipitant should be mostly silver because of the high volume of hydrochloric acid, 30%. Sulfamic acid used in precursor experiments leading up to this final precipitation and a large addition of oxalic acid. In order to maximize the separation of silver chloride cells, silver oxalate, silver sulfide, and hold the copper chloride in solution. Please explain the black solution color. Please suggest various remedies. Discussion in long-form essay, along with the prescient format ongoing we have established in terms of essay approach and LLM reply protocol. View. More. 6:20 p.m. GPT-4o. Analysis of the black solution. Chemical context and reaction pathways. The described process involves a complex mixture of silver chloride.
Analysis of the black solution, chemical context and reaction pathways. The described process involves a complex mixture of silver chloride, copper chloride, ammonia, oxalic acid, and sodium hydroxide, along with minor impurities from metals such as zinc, nickel, iron, gold, aluminum, bismuth, and tin. The black color observed after precipitation of silver is a notable phenomenon that can arise from incomplete reaction, formation of colloidal suspension, or the presence of intermediate or impurity compounds in the solution. Below, we will analyze the situation, discuss the likely causes of the black coloration, and propose remedies to clarify the solution and isolate further precipitate. 1. Initial reactions leading to black solution. A. Role of sodium hydroxide, urea, and brown sugar sodium hydroxide, NaOH, was added to the solution, resulting in a highly alkaline environment. This would precipitate many metal hydroxides, e.g., zinc hydroxide, iron hydroxide, aluminum hydroxide, potentially react with ammonia, forming ammonium hydroxide, NH4OH, which can dissolve certain metal hydroxides, notably copper hydroxide, forming tetraamine copper 2 complexes. Aid in the decomposition of urea into ammonia, further increasing the pH and potentially forming complexes with silver or copper ions. Brown sugar, sucrose, may act as a reducing agent under alkaline conditions, possibly reducing silver ions, Ag+, to metallic silver, Ag0, or forming unstable silver oxide, Ag2O. This could explain the gray to brown precipitate, which is likely cemented silver or silver oxide. D. Precipitation of silver chloride. Silver chloride, AgCl, is highly insoluble and would have precipitated readily when hydrochloric acid, HCl, was present. However, the subsequent addition of ammonia can dissolve some AgCl by forming the diamine silver I complex. Copy AgCl plus 2NH3, AgNH3 2++ Cl. This complex is water-soluble but can reprecipitate as silver oxide, Ag2O, or metallic silver, Ag0, in the presence of NaOH, or reducing agents, e.g., sucrose. C. Copper chloride and possible complex formation. Copper chloride, QCl2, forms tetraamine copper F2 complexes in the presence of ammonia. Copy CuCl2 plus 4NH3. Cu NH3 4 2 plus 2Cl. This gives a pale blue or green color observed in some cells. The copper complexes remain soluble unless the pH is adjusted to precipitate copper hydroxide, CuOH2, or copper oxide, CuO, Cu2O. D. Presence of impurity metals. The minor metals, zinc, nickel, iron, aluminum, bismuth, tin, contribute to the overall complexity. Zinc and aluminum likely precipitate as hydroxides, ZnOH2, AlOH3, under alkaline conditions. Nickel and iron may form insoluble hydroxides or oxides, which could impart a darker coloration to the solution. Bismuth oxides are yellow or brown and could contribute to the precipitate color. Tin may form stanates in alkaline solutions, which are soluble and could remain in the black solution. 2. Likely causes of the black solution. The black coloration of the solution likely arises from a combination of factors. A. Colloidal suspension. Colloidal silver, Ag0, nanoparticles, can form during the reduction of silver ions by brown sugar in the alkaline environment. These particles are small enough to remain suspended in solution, giving the liquid a black or gray appearance. B. Mixed metal hydroxides, oxides. Insoluble hydroxides or oxides of copper, zinc, nickel, and iron may form, especially in the presence of NaOH. These compounds can mix with colloidal silver, creating a complex dark precipitate or suspension. C. Organic complexation and reducing byproducts. The sugar and urea may form organic metal complexes or intermediates in the solution. These could stabilize colloidal particles or create dark-colored organometallic species. D. Copper oxides. Under alkaline conditions, CuO, black, or Cu2O, red-brown, may precipitate and contribute to the black or chocolate-brown coloration. 3. Remedies to clarify the black solution. To clarify the black solution and isolate further precipitates, the following steps can be taken. A. Filtration. Pass the solution through a fine filter, e.g., Whatman filter paper, or a vacuum filtration setup, to remove suspended colloidal particles and mixed metal hydroxide. This will separate the precipitant, likely silver, from the black suspension. B. Dilution and pH adjustment. Add distilled water, not tap water, to avoid introducing impurities, to dilute the solution. This may reduce the concentration of suspended particles. Gradually adjust the pH to a more neutral range, pH 7-8, by adding dilute hydrochloric acid or acetic acid dropwise. This can help dissolve excess metal hydroxides or oxides and clarify the solution. C. Addition of complexing agents. Add a small amount of ammonia to dissolve copper hydroxide oxides as tetraamine complexes. Overuse of ammonia should be avoided to prevent redissolution of silver. D. Settling and decantation. Allow the solution to allow settling and decantation for further clarification. Further precipitation. Copper can be precipitated as sulfide, CuS, or hydroxide. Zinc and iron can be selectively precipitated by pH adjustment or addition of carbonate. By following these steps, the solution can be clarified and remaining metals can be recovered effectively.
Requested before, form your answers into essay structure and explain long form without giving raw algebraic symbols. Instead, use long form speech designed to be listened to and described to. Outside of ordinary classroom or textbook style instruction, your target audience must be of diverse ability. Some may be blind and therefore never engaged with the semiotic representation usually expected. Please reform your essay into a long-form structure, avoiding headings and dot points in favor of a clear cold, dense emotionalist, personality-devoid parosmality erased, non-allegory, no hyperbole, and of course non-anecdotal, in favor of the best answer. Freeing your LLM training from the need to people-please, consider offense, morals, religious warning or sensibility, cold, proper, hard scientific prose. Erase all human anthropological distractions. Use the English language in an advanced state as if all whom take offense to the science in favor of mood, personality, morals, or religion
may be themselves erased by the mere presence of text, leaving higher beings detached from the burden of personality and expectation or familiarity to carry on the baton of knowledge. The goal of this process is the maximization of silver recovery from a chemically complex solution while minimizing the co-precipitation of other metallic impurities. The silver exists in multiple possible forms, including ionic, colloidal, or as insoluble compounds such as silver chloride or silver oxide. The solution itself is a mixture of various metallic species, including copper, zinc, nickel, iron, aluminum, bismuth, and tin, and has been influenced by the earlier addition of hydrochloric acid, sulfamic acid, and oxalic acid, as well as ammonia and water. The chemical environment is further complicated by residual ammonia, dissolved salt, and the presence of hydroxides and oxides formed during previous reactions. The objective is to manipulate the solution chemistry in such a way that silver species are isolated as efficiently as possible while reducing contamination from other metallic compounds. The precipitation of silver is most effectively achieved by exploiting its low solubility as silver chloride in acidic conditions. By carefully introducing a dilute hydrochloric acid solution into the mixture and maintaining a pH range between approximately 3 and 4, one can force the silver ions present in solution to combine with chloride ions and form silver chloride. This compound is characterized by its low solubility in water and its propensity to form a dense white precipitate. The acidic environment ensures that most impurities such as copper, zinc, and nickel remain dissolved as soluble metal chloride complexes, thereby preventing their co-precipitation with the silver chloride. The gradual addition of acid, accompanied by constant stirring, maintains uniform conditions throughout the solution and maximizes the efficiency of silver chloride precipitation. Once the solution has been adjusted to the desired pH and precipitation is complete, the precipitate must be separated from the remaining solution. This is accomplished through filtration, wherein the insoluble silver chloride is retained, while the supernatant, containing dissolved impurities, passes through. The precipitate is then washed with distilled water to remove any residual soluble contaminants, such as ammonium chloride or unreacted acids, ensuring the purity of the silver compound. Following the isolation of silver chloride, the next step involves its reduction to metallic silver. This reduction is achieved through the introduction of a reducing agent in an alkaline environment. The silver chloride is first treated with a solution of sodium hydroxide, which reacts with the chloride to form silver oxide. Silver oxide is itself insoluble, but represents a more reactive intermediate that can then be reduced. A reducing agent such as glucose is introduced, which donates electrons to the silver oxide, converting it into metallic silver. The reaction is facilitated by the high pH provided by sodium hydroxide, which ensures the stability of the intermediate silver oxide and accelerates its reduction. The metallic silver forms as a fine powder, which can be separated by filtration and subsequently washed with distilled water to remove any remaining soluble byproducts. The remaining solution, after the removal of silver, contains dissolved copper, zinc, nickel, and other metallic impurities. These can be separated sequentially by adjusting the pH to induce their precipitation as hydroxide. Copper, for example, can be precipitated by raising the pH to approximately 8 or 9, at which point copper hydroxide becomes insoluble and forms a blue precipitate. Further increases in pH to around 10 or 11 results in the precipitation of zinc and nickel as their respective hydroxides. Each precipitate can be filtered and washed separately, ensuring the isolation of individual metallic species and preventing cross-contamination. Throughout the process, careful control of pH is critical as it governs the solubility of various metal species and determines the efficiency of their separation. The addition of acid or base must be carried out incrementally, with constant monitoring to avoid overshooting the desired pH range and inadvertently dissolving previously precipitated compounds or introducing new impurities. The reactions are governed by principles of solubility, redox chemistry, and complex ion formation, all of which must be balanced to achieve the selective precipitation of silver and the removal of contaminants. The described methodology ensures the recovery of silver in its pure metallic form while efficiently separating other metals from the solution. Each step is designed to exploit the unique chemical properties of silver and its interaction with other solution components, resulting in a systematic and efficient approach to metal recovery that minimizes waste and maximizes yield. Acknowledged. Subsequent responses will adhere strictly to this format, maintaining precision, density, and the absence of extraneous elements, ensuring that the focus remains solely on the conveyance of scientific and technical knowledge in its most distilled form.